Okay, let's now take a deeper look into PCA, or Principal Component Analysis. So we have two features, x1 and x2, and the green shape here represents the data. Okay, so what we're gonna do is we're gonna choose two unit vectors, a1 and a2, in the direction of the biggest variance. Yeah, so the biggest variance is clearly around this axis. So we choose a1 along this line, and the next biggest variance is this one. Yeah, so our a2 vector goes along that line. Yeah, a1 and a2 are perpendicular to each other, so they are independent. The first thing we need to do in PCA is mean normalization, meaning from the features we're gonna subtract the mean, so that the mean is 0 and the data is centered around 0. So we take a vector here, the red vector is x minus mu, so it's a mean normalized vector. And what we're gonna do is we're gonna project that vector onto the a1 axis. And when we say projection in math, we mean dot product. So we're gonna calculate the dot product of a1 and x minus mu, and we're gonna call this z1. Remember, the outcome of a dot product is a scalar, so z1 is a scalar. Now we're gonna try to find a in such a way that the variance along z1 is maximal. Yeah. So let us now make that calculation. We've seen that z1 is the dot product of these two vectors. X minus mu is also a vector. So this is the unit vector, remember, is fixed. And this is a column vector of random variables. Now what we're gonna prove is that the covariance of AX equals A transpose covariance of X times A. Covariance of X means the covariance matrix, and we denote by big sigma. So this is equal to A transpose sigma A. Yeah? So that is an intermezzo. We're gonna try to prove this first before we continue. Just a little bit of a background, and again, if you've not looked into the linear algebra refresher as well as the statistics refresher, please do. But basically, the variance is a measure of the spread of the data. Yeah? The definition of the variance is the expected value of x minus x expected value, yeah? Which is x minus mu. The expected value of x, in our case, we call it mu, is the mean. Yeah? So it's a measure of the spread. We also know that the expected value of ax equals a expected value of x. This is also something we're gonna need. So we are able to bring this a to the front. And also what we're gonna need is that the square of the norm of a vector is the same as the vector dot product with its transpose, or the other way around. Yeah? These are things we need to remember. Our feature vector x is d-dimensional, goes from x1 to xd. And then we're going to define the variance of a vector. Yeah? And the variance of the vector we also call the covariance of the vector. And that we denote by the sigma. How do you have to picture this covariance vector? Well, it's relatively simple. On the diagonal you have the variances of your features, so from x1 to xd, and on either side of the diagonal you have the covariance. It's how these features change relative to each other. So covariance x1, x2, and we go back to all the way down covariance x1, xd. Here on the rows we have covariance x2, x1, right? And all the way down you're gonna have covariance xd, x1. Yeah? So this is how this covariance matrix is built up. So covariance AX is actually the variance of AX. Yeah? And we're gonna use the formula of the variance of AX. That means that we're gonna replace in this formula X by AX. Yeah? So it's the expected value of AX minus the expected value of AX. And here exactly the same, but transpose. So we went from this formula to this one, and we replaced here X by AX here. And now we're gonna use this rule here. We're gonna put the A outside of the expected value. So equals expected value of AX minus A expected value of X. Okay, and here the same thing, AX minus A expected value of X transpose. Yeah, and this we close here. Now you're gonna see the two A's here. We put this A outside of the brackets. So equals expected value of A. And then we have X minus expected value of X. Yeah. And the same on the transpose side is X minus expected value of X. Here we go. Transpose, and then we close the brackets. Now we've also seen in linear algebra that AB transpose equals B transpose A transpose. So we gotta swap the A and the B. So this one here becomes X minus expected value of X transpose A transpose. Okay, this is exactly what we applied here. Now this A here we can immediately take out of the brackets as well, so that in the end we have A, this A goes outside, but here if you look at this one now, together with this one, this is nothing more than the covariance of X. Yeah? This is exactly the definition of the variance, and in our case, because we deal with vectors, it's covariance. So equals A, and then we have the expected value of this and this, which is the covariance of X, times A transpose. This is exactly what we try to prove here. Yeah, so let's close this intermezzo and let's now apply that formula to this. But before we're gonna do this, we're gonna look at a constraint. There is a constraint, meaning that A1 transpose times A equals 1. This is per definition. Yeah? You take a vector transpose times the vector is 1. Yeah? This is a definition, and we've seen that in linear algebra as well, because that times that, these are unit vectors. Yeah, so this will be, just to make it a bit more simple, we can use it there, is A squared. And A is the unit vector, so it will be 1. Okay? Now, we want to maximize the variance. We have a constraint. So that brings us to the Lagrange multiplier. A maximization problem with a constraint. And the Lagrangian is going to be, we're going to apply this formula on there. It's going to be A1 transpose covariance X, because the covariance of X minus mu is the covariance of X, times A1, minus lambda, and then we have this expression A1 transpose times A minus 1, and we have to now differentiate or take the gradient of the Lagrangian and set it to 0. So let's take the gradient for A1 transpose times A1 is A squared, is A1 squared. So it's 2 times covariance X A1. Yeah. Okay, minus this plus lambda is a constant, so a gradient is 0. So it is minus, and that's exactly A squared, A1 squared again, 2 times lambda A1. Yeah, and we set that to 0. Okay. Now we see we can eliminate the 2's, so that at the end we have covariance of X times A1 equals lambda A1. And basically what this formula is saying, yeah, and we've seen this in the linear algebra refresher, that A1 is basically the eigenvector of the covariance matrix. Yeah?